Hi, my name's Karsten Wolf, and I'm an associate professor at the Norwegian University of Science and Technology. In addition, I've had a hobby for a long time, and that is to try and figure out how can we make analog circuit design differently, simpler, faster, better. And I wanted today to give a short overview of my current thinking on this topic. First, a little bit more about me. So, why do I feel I have the right to actually talk about this? Or why do I actually, anybody has the right to talk about it, but why do I think that what I say actually is true and could influence others? So, this is my life. Back in 1986, I got my first PC, and well, then education happened, and I started working in the semiconductor industry, and I still work for Nordic Semiconductor. And in beginning for Nordic Semiconductor, I did analog design, so ADCs, DC-DCs, and those type of thing. Now, in 2000, let's see, 12, 11, 13, 14, I got the opportunity to do a part-time postdoc. And at that time, just finishing a couple of rounds of ADC design, I sort of wanted to find a slightly better way. And I had been thinking for a while about how to do this. But then I really got the opportunity to spend a few days a week on really trying to make some progress. And that's a little bit what I want to tell you about today. So before I get down that path, I want to explain how I see our roles in the universe of integrated circuits for analog design, or actually most design. For academia, professors, we try and guide our students on what we know to be possible and what we know to be impossible, and then maybe some hints on what could be possible. For PhD students, we really try to get them to explore the unknown and figure out something new. Now, they don't have to make things actually work. They don't have to work in the real world. What we ask them to do is just demonstrate that something could be possible. Because I consider it the job of the industry to take what is possible and make it maybe complicated to do, and then in the end make it easy so we can produce products, sell it, and copy it in the millions to billions of products. When it comes to master students, I expect them to maybe learn most of what is possible, and for bachelor students, I expect them to learn how to make the complicated easy. Now, the world is analog. That's just, it is. There's nowhere around that. Fact. And it's governed by laws that we have discovered over, well, I guess hundreds of years. And we've chosen to describe these laws, or actually, the only way we know to describe these laws are in the mathematics. And particularly for what we call the Maxwell equations, which describe the relationship between electric fields, magnetic fields, electric charge or charge density, and current density. Those can be, well, horrendously complicated, as you see in the slide. To figure out all those four components, you actually have to solve Maxwell equations. And for any student that has tried to do that, it is not trivial. It is hard to find actually how to do it for a real world scenario. Now you can do it numerically and you have tools to do that. At a smaller scale, when we move down into the integrated circuits and semiconductors, we move into the quantum realm. And here we are governed by how we think the small world works. And when I say how we think it works, we are pretty sure because we haven't found any evidence that the laws of quantum mechanics or the rules that we have for quantum mechanics is wrong. Now, fundamentally, the equations of quantum mechanics is actually slightly simpler than Maxwell. Um, the equations of quantum mechanics are linear differential equations, but still what they tell us is quite complex. So such things that the probability amplitudes, so not the probability of finding an electron, but something that we've chosen to describe as the probability amplitude of an electron, is given by a complex function. And it's really, if you take the norm squared of that, you can find the amplitude. Now, finding this wave function is not necessarily trivial because it's not a single wave function for a single electron. Electrons may interact with the world around them, and you get a superposition of wave functions. And then computing the time evolution, how this evolves, and what states are available, I guess you need to involve Schrödinger. And for semiconductor physics, how many electrons you have in a conduction band is a function that depends on the energy levels in the lower and higher ends of the conduction band and the density of energy levels multiplied by a probability of an electron being in that energy level. Now that probability is given by Fermi statistics, which is this equation. So the real world is analog. However, most of the complicated computing we do today is done in the digital world. And in the digital world, an abstraction happened. I don't know when, but probably back in the, well, a long time ago, for certain back in the 70s. It was discovered that if you simplified and you only had two states, true or false, you could actually make circuits that do that, call it inverter or logic gates. And if you do that simplification, you can build actually most of the complex computation that we do in the world based on this simple abstraction. If you have the function that is equal to not a and b, which you can see the truth table for in this figure, then you can do anything. You can do all calculations. Now that abstraction enabled something cool. It enabled the fact that when we describe digital circuits, we don't do it in transistors. We do it in a hardware description language. It's not the same as well, it is a programming language, but it's not the same as Python or C++. It has similarities, but there are some fundamental thinking differences. But the key thing is that once you have this code, you can actually reuse somebody else's code. So my claim is that it's easier to stand on the shoulder of giants. But that hasn't really happened for analog design. Analog designers, well, we try and teach them how they should deal with the real world and simulate and make schematics and architectures and structures and different type of example circuits. But in the end, they have to do it on themselves. And that hasn't really changed. Now, of course, these days we do as much as possible in the abstract digital world. But we'll always need something to interact with the real world. This is a picture from a training material that I think Walter Kester, or don't name me to the wall on the name, but this is the world's first commercial ADC. It was a SAR ADC, and we are still making SAR ADCs. And we're still making analog interfaces, both for input and also controlling the world through digital to analog converters or radios. Or there's always some sort of analog interface on a chip where you have to think as an analog circuit designer. You have to deal with the real world. So, fundamental statement, there will always be analog circuits. It doesn't matter what technology you will be in, whether it's, I guess most people think that Moore's Law is running out of steam, but there will always be analog, whether we make them in CMOS or we make them in carbon nanotube based circuits or whatever the future holds. There will be analog circuits. But why is it so hard to reuse analog? Well, it really comes back to the fundamental nature of analog circuits are in the real world and affected by all the different components of the real world. They're affected by, for example, Maxwell's equations, how the electric fields and magnetic fields and the charge and the current density changes. Now you can put inputs and outputs on an analog module also, but you cannot expect that using the same analog module in a different environment, it will behave the same. Because the analog inputs and analog outputs, well, they depend on what's sent. For example, an analog input, it depends on the output of the previous block. And even for some analog, it has inputs that are not even on the module. It can be, for a radio, it can be the magnetic fields coupling from the current spikes in a DC-DC on one side of the chips to the inductors inside the radio. It is horribly complicated because it lives in the real world. Now you can simplify that somewhat, by trying to contain and control the interfaces and making sure that you describe how to integrate IPs and things like that, but it is always hard, which means that we always need to think about how to integrate IPs in a new product. A second thing is that the digital designers, they can reuse virtually their same RTL code and then jump from, let's say, 16 nanometer to 5 nanometer to 7 nanometer, and the code may stay the same. However, for analog, the fundamental building block of the circuits that we have is the transistor, and that is not the same. It is fundamentally different. It has different physical dimensions, so the properties are not the same, which means that we have to resimulate when we go to 5, from 5 to 7, or even between two technology nodes that are called 22 nanometer, because if they come from two different factories or foundries, it's going to have different physical properties. Nobody makes the transistors exactly the same. And all this makes it hard. So the life of an analog designer, it sort of starts with, well, we draw our schematic. Maybe before this we think quite a bit. Whiteboards, talk to people, etc. Look in books. But at some point we start drawing a schematic using the transistors in that particular technology. Once we have something that we think can simulate, we use the models. So these are mathematical models of how we believe the transistor operates in the real world, and we use computers to then calculate whether the circuit that we hooked up actually works actually works is wrong. We try and simulate, and if the simulation works, we assume that the circuit is probably going to work in the real world. So we make a schematic and we simulate. Now, it's not one simulation, because we also have to account for the fact that every single chip is different, the temperature is different, the voltage supply might be different, all the environmental conditions and that affect the real world operation has to be simulated. Once we're satisfied with that, when we're pretty sure the circuit we have is going to work, then we do the layout, which is actually a bit stupid, I think. First we draw the schematic, and then we draw the exactly same thing, just with polygons. And this is to instruct the foundry, how are you going to make our circuit? And this is necessary, because we can't send the schematic to the foundry, the factory. They don't know how to do that based on the schematic. Nobody knows how to automatically generate layouts from a random schematic. Many people have tried, but so far, over the past 70 years, nobody has succeeded. And if you ask people that have been in the industry for long, if you tell them, oh yeah, I'm making an automatic layout generator, they will most likely laugh of you. But anyway, we create another representation of the circuit, and then we simulate again, because now we can have an idea of what is the parasitic capacitance, what is the parasitic resistance in the metal wires, what's the changes in the transistor due to the physical location of the other transistors. And then once we're pretty sure it's okay, then we can send it to the factory and we can measure it. And once we measure it, that's the point where we can be reasonably certain it is going to work. Now, this is a very long process, this design of analog circuits, and especially the fact that you have to do the same type of operation every time you switch node. Every time you jump from a node to another node, or slightly different node flavors, you have to do a lot of changes. And this bothered me because I'm the type that once I've done something and I've done it well enough once, I don't want to do it again. I want to do something new. I want to learn something new. So I started thinking about a long time ago, how can I actually simplify this? Is there a way I can do it faster? So the trigger actually was back in, this was around 2008, 2009. I wrote a paper together with some other people, and one of them was Lenny Levin. Now, he is an analog designer, worked for many years, and he's, I believe, also the one that created the analog to digital converter in Hubble. So he knows what he's doing. And I had a look at his layout. So he did a presentation here in Trondheim in 2009, and he showed this part of the layout. And it showed sort of extremely regular structures. And my first thought sitting in that meeting room was, wait a minute, this layout, I can generate this. I can figure out how to code up a program to generate the layout for this. And that's sort of was the initial spark. Then a few years of trying sort of making not P-cell generators, because I were writing things in Perl, but trying to make things that can sort of generate op amps or generate transistors. And I use that in my design also. And then in 2014, I got the opportunity for the postdoc, but then I didn't want to just continue doing automatic layout type of stuff. I wanted to actually see, could I rethink a bit how I did the design phase such that I can create something that was portable, something I can respin in a different technology or port to a different technology relatively fast. But I didn't want to do a design that was just an ADC. It had to be state of the art, because otherwise, why would people use it? So the problem at that point was, at that point in time, there was not that many efficient sort of high-speed ADCs. So I thought, okay, let's try and fill that hole. Now, picking the architecture for the ADC was pretty simple. At that point in time, it was successive approximation ADCs. So a guy called Dietel Drexelmeier, back in, I don't remember when this was, I think it was 2006. He published this paper at AIC2023, and he sort of brought back to life the good old successive approximation ADC, and which today is quite prevalent. So that was the architecture. Now, plan. This is a bit of a non-causal plan. This is where the plan ended up. This was where I ended up. It's not exactly the plan I started out with. So I wanted to create ADCs. Now it happened to be that the 9-bit ADC was the best performing in terms of figure of merit. So that's what the plan ended up being. Anyway, how do you actually make ADCs fast compiled? Well, basically try and spend half of the time trying to make a system to compile it, and spend half the time trying to design it, figuring out how it should look and adding some new circuits and so we could publish it. Um, and I ended up with a system where, so first of all, I wanted the script itself to be as independent of tool vendors as possible, because I'd used at this point in my career both mental graphics and cadence, and I could see a point in time when I'd had to switch to something else. So I didn't want to lock myself to cadence specifically. So I didn't want to use skill. I didn't want to use the format, because actually I couldn't at that point. I didn't have access to the open access library either, so the description of the files in cadence. So I wanted to be totally open. And Spice netlist, well, everybody supports that. That's fine. That's old. And that gives me the connectivity and maybe some more information. But I needed some meta information. And meta is just a database of information. So I chose JavaScript object notation, which is it's a JSON file. This had the object hierarchy and the dependencies and inheritance and other things that I brought with me from object-oriented programming. This initial Perl script that was about 16,000 lines of code, it worked okay, and it was used for multiple tape outs. Now, in addition to the technology independent stuff, I also needed something to explain how do I create not a transistor, but what are the rules in this technology? Or what rules do I have to follow to make something that is DRC LVS clean? And that's baked into a technology file, which is also a JSON file, very, very small one. So, one of the things I did was I knew I wanted to port between different technologies at some point. So I wanted the description of the transistor to be as simple as I could make it. Now, I had tried to make sort of P-cell type of stuff, building a lot of information into the Perl, but I realized at some point, I think, or it happened on it by chance, that maybe it's better to just make this really, really simple. And I ended up coding up the transistors by just saying, this is my OD layer, my diffusion or active region. And where there's an X, draw a rectangle. Where there's not an X or a dash, then don't do anything. And add context where there's a C and so on. And when you do that for, in this case, OD, poly, and metal 1, you get a structure that looks like this through this compiler. But in addition to just having transistors, you have to have a way to connect them to each other. So this is the example of an inverter. And let me actually go full screen on that. So you have to route it. And that means you have to know maybe the connectivity. And at least you need to know also how to place it. So you need to know which order to place the transistors. Now, the order of the placement, that was pulled directly from the Spice netlist. So the compiler would read the subcircuit and then see, okay, the first thing is a NCHDL, an NMOS transistor. And it would use the first part of the instance name as sort of I call it a group name. So if the group name was the same, you would start with the transistor here. If the next group name was the same, you would add it on top. But since this group name for the PMOS is different, it adds it on the side. Now, schematic coordinates, I had an idea early on that I could also create readable schematics from this. That didn't work. I couldn't really build in sufficient information into the JSON file to create readable schematics. I still don't know the best way to do that, but what I'm leaning towards now is it's probably better to have a slightly different order of things. So schematics is a good way to think. But in order to make something that is actually compilable, you have to draw the schematics in a specific way with certain names for the instances and so on. So it's maybe a chicken and egg problem, and I think currently I'm at schematics should come first, but drawn the right way so it becomes easy to compile the circuit. For connectivity, it is using a strategy that comes from ticks actually. So I'm also fond of regex. So in this case, it will search through the hierarchy and it'll find rectangles, or actually ports, for the MN devices that are called D. So that's this node. And then it'll do straight, up or down, straight, route, and that's what you can see here. Straight, and then it doesn't really go up or down because it's supposed to go straight over, because it's routing to this MP rectangle. Now this is an incredibly dumb algorithm. It has no intelligence. You can't give it 2 ports and tell it to automatically. And it will create shorts, it will create LVS errors. So it needs a designer to really say, okay, I'm sure I want the routing to go, let's see, to go straight, up, down. And as long as that is okay, then that's what it does. Of course, you can check the LVS and DRC yourself afterwards. Now, all that work ended up in many ADCs. So the first one was created around August, and then by tape out, I don't remember when tape out was, a little bit later, but it was quite short time to generate all the different ADCs. And the ones I ended up publishing was this 9-bit here and this 9-bit here. This 9-bit IO voltage was actually added just a few days before tape, or just a few weeks or something before tape out. It ended up being successful and people liked it. So I got the opportunity to write a paper in Journal of Solid State. And I really think I hit the original goal of showing that you could actually get similar performance as state of the art with a slightly different way of making ADCs. And I'm not going to claim it was easier, but I can promise you it was easier to port. Since that time, I've had a few students. One of them was Haral. He also did compile ADCs and he really took it to a next level when it comes to complexity. So this was a noise-shaped ADC, and although reusing quite a lot of the code for, well, reusing the compiler, he was able to actually also add loop filters and op amps and stuff. Although he did have to do some changes on the compiler. This was a very good paper, by the way. Now, since then, I guess after publishing and after ending the postdoc, I had less time to focus on that part of my life. I focused more on work at Nordic, and I really didn't see the next step. But then around, well, I guess 2020, I went back to NTNU a day a week, and then 2021 started teaching, and then this summer, I've been thinking about it for a while, I figured out that, well, there is this open source PDK, Process Design Kit, from Skywater out there. Maybe I could port my ADC to that, was my thought sort of earlier this year. And during the summer holiday, I finally had some hobby time to spend on this. And it was actually not as trivial as the other technologies. It was a bit harder actually, because I also had to port to different toolset. No longer could I produce skill as the output. I had to produce magic files and XChem files. But at the end, it's now available on GitHub, the ported version. I haven't taped it out yet, because before I tape it out, I want to figure out exactly what I want to put on the chip. But it has been a good way to do SARS. Now, I wanted to touch on what have I learned, I think. What choices were right and so on. Now, a really, really good choice early on was to make the lowest layer, the transistor, very, very simple. And actually, for most of the designs I do, I only have a few, maybe 2 NMOSes and 2 PMOSes. And I build all the different combinations of transistors from those 2 structures. Which means that you take away flexibility. And flexibility is the enemy of automatic layout generation. But the super simple transistor was a very good step. Now the one on the left here is the transistor from 28 FTSOI. No, sorry, this is the Skywater one. On the right is the 28 FTSOI. On the left is the Skywater one. And here you can see 3 dots. That's because the Skywater one is much bigger. It was a bit harder to figure out how to do the layers correctly in Magic, because it has different names for diffusion contacts versus poly contacts and so on. But it was indeed possible. Now the good thing about that, once I've been able to port the transistor and make it DRC LBS clean, then most of the other things just fall into place. So for example, for a larger circuit, like in this case it's the comparator half circuit in the SAR, that's almost the same. You can see these two are different. So this is from the left is from 2016, the right is from 2020. So there are differences, but for the important stuff, the routing, which is the add directed routes, you can see that is, I believe actually, I haven't checked that it's exactly the same, but it's almost the same. And there's minor tweaks. So this is also different compilers. So this on the one on the left was made for the PERT compiler, so the input to the PERT compiler, while the one on the right is for the current C++ compiler. So I also learned that using this system is hard. I'm able to use it effectively, and I know of a handful of other students that have been able to use it. And I don't think anybody would claim that it's easy. It is actually quite hard. But the ones that have used it and are using it for ADCs are motivated by the fact that, yes, it's harder than drawing a schematic, but you only have to do it once. And it allows you to delay changes or delay decisions, like technology node a bit. Maybe you can more easily change nodes. It also allows you to iterate on the design on a completely different scale. And it reduces the fear of changing major things late because of layout, because you can easily replace key components of the circuit and just redo the layout in seconds. If you want to look more into this and the work that I've done, currently I'm working on, well, how to teach students. And I'm using the repository called AIC, and there you can also find the ADC and the compiler and all the stuff. I'm not going to claim it's the best documented system in the world yet, but it is there and it's open. Right, that's what I wanted to go through today. Have a good day.